equation, which will be n squared, which is 3 squared, which is going to give us 9 orbitals. So the point I'm trying to make here with this, if you can kind of see, I started to see the pattern here. If you look here at these answers we got for n equals 1, you're going to have 2 electrons in 1 orbital. And then if you do, so 2 divided by 1 obviously is 2 electrons per orbital. And then this is the same thing here. 8 divided by 4 is 2 electrons per orbital. So that pattern follows basically, no matter how many energy levels you go, you're going to get 2 electrons per orbital. So that's going to be really important for lecture 9 when we're going through, we're going to be going through orbital diagrams, which, let's just clear all our drawings. The orbital diagrams are going to look like these little boxes that you've seen, like this. Draw that a little bit bigger. So the orbital diagrams are going to look like this. And this box represents 1 orbital. And so, and this is going to represent 1 electron. And in every box, you're going to see either 1 electron or 2 electrons, but you'll never see more than that. You're always going to get 2 electrons per box when we use this type of notation. And so just remember that as we're going through that orbital diagram notation, that's why we're splitting into 2, is because there can only ever be 2 electrons per orbital. Okay, a little bit of a foundation there. All right, part of that as well, I'll just explain beforehand. One of the quantum numbers that defines why there can be 2 electrons in 1 square like that, you would wonder because they're both negatively charged because they're electrons. The reason they're pointed up and down like that is because it's the ms quantum number, which is the spin, and that can always be only plus 1/2 or negative 1/2. So that's why there's 2 electrons and they're facing 2 different ways, and that they can coexist in 1 orbital is because of the quantum number ms, which signifies their spin. So if they're spinning opposite of each other, they can be in the same orbital together. And just know that, like we've already discussed, there can only ever be 2 per orbital. Okay, let's clear this. Okay, now moving on to lecture 9. We're just going to talk a little bit about the different orbitals that are possible in each energy level. So we have the energy level, which is N. That's our energy level. We also have the quantum number L, which is the orbital, or the shape, I guess, of the orbital. And the different L's, the numbers for L can be, 0 to n-1. We usually only deal with 0, 1, 2, and 3. And each one of those are signified. They correlate to S, P, D, and F. So those are the different orbitals that we deal with in this class and that are in the periodic table. There are more complicated ones, but we usually just deal with the quantum number L. We only deal with these right here, which are 0, 1, 2, and 3 orbitals. But we just represent them with letters because it makes the notation a lot easier. So now I just want to explain how this works into our lecture. So we're going to talk a little bit about each one of these orbitals first. So the s orbital is a spherical shape. So it's going to look a little bit something like this. If you have, we'll just draw a circle. It's going to look something like this. That's what that orbital is going to look like. And then you have the p orbital, which is going to be just the s orbital cut in half. And it'll look kind of just like a dumbbell shape like this. You just have two that look like they're connected together. And then you have the d orbital. That is going to look like 4-leaf clover like that. It's almost like the p orbital, but just cut in half again. And then you have the f's, which are a lot more complicated, which are just going to look pretty complicated like this. You might have the bigger ones like this connected to smaller ones. I have 3 right here connected to 3 big ones, and then the same thing on the other side. Okay, so those are kind of the general shapes. So these s orbitals right here, they're going to be correlated to a smaller energy level. And then as we move to p and then d and then f, the energy level on those orbitals will grow. So as the L number gets higher, like 0, 1, 2, and 3, it correlates to our energy levels, how large they're getting. So that's going to help us as we move towards the periodic table. So I'm going to do a drawing here. I guess first we'll go over how these different orbitals will fill up with those electrons that we talked about. Here, let's do this. So the way we fill these different orbitals, there's some rules that we use for these different orbitals and how we're going to fill them with our electrons. So remember, there's two electrons per orbital, and then there's subshells within those orbitals. So let's just go through the rules real quick. So there's the off-ball principle. Now this rule says that the electrons are going to be placed in the lowest energy orbitals first. So I guess a good way to remember that is if they give you the N and the L, the lowest N plus L value is where you're going to put your first electron. This is going to be your first electron. Will always go in the lowest orbital right there. And then after that, we have the Pauli exclusion principle or rule. And this says that this is what I just explained. I just explained like the reasoning behind it and kind of the math, but the idea is that only 2 electrons in an orbital. Okay, and then the other rule is going to be Hund's rule or Hund's principle. This idea is that those electrons are going to fill up orbitals by themselves before pairing. To kind of show that, the idea is that, like, if you have, let's just say 2p, which is going to have 3 subshells, but it's going to hold 6 electrons. If you have, for example, 3 electrons that you need to put in the 2p orbital, the idea is that those 3 electrons would separate themselves and be in 3 different subshells there before they're going to pair up like this. Just draw a bad example here. So they would do this before they do this. So they always want to be by themselves. And that's the idea. They'd rather be by themselves first. Okay. So with that background, now we can kind of hop into the periodic table and how we're going to be able to read the periodic table, kind of like a map, to figure out which orbitals we'll put these electrons in and like how many electrons each element has, and just kind of what the base is. So I guess we'll just clear this. 1 second. Let's get this. Okay, I'm gonna do a drawing here. It's gonna just kind of be kind of a low down drawing of the periodic table here, but stick with me, it'll make sense. Okay, so the kind of the shape here of the periodic table looks like this. You got this, and you're going like this, and more, and you're down. Okay, so I'm gonna divide up the periodic table into the different orbitals that correlate with each area, so that you'll kind of know where each orbital, where each element falls within these orbitals and where their electrons are going to be. So knowing what we know now about the different orbitals and how many electrons and how to find how many electrons will be in each orbital, let's go here. So the patterns that the periodic table follows, we'll just start here with the transition metals. So the transition metals here in the middle, these are going to be our d orbitals. And the d orbitals will have 10 electrons. And their energy level will always be the number of the row minus 1. So the rows work this way, obviously, on a periodic table, and then groups are this way. So the number of the row, it'll be the number of the row of the element. Minus 1, and that will tell you the energy level. And then you'll know that in each d orbital, there's going to be 10 electrons in each of these. In other words, you'd have 5 subshells. So it would look like this. Just so you know, 1, 2, 3, 4. And then you'd have 2 electrons in each of those subshells for a d orbital. So that's what this is going to be right here. And we'll get back around to these down here on the last 2 rows, those extras that are radioactive elements that are going to be down here. But I'll come back to those in a second. So that's our d orbitals. And remember that D is equal to, is our quantum number L. And if it's D, we know that D is equal to 1, or L equals 1. So now we're going to do this right here. These all right here are going to be our s orbital, the spherical shaped ones. These ones are going to have 2 electrons, like we found out. And then we're going to do, their energy level should equal just the number of the row that the element is in. Okay. Yeah, also right here, helium, he's all alone over here by himself with the noble gases. He's also going to be considered an s orbital. So he'll follow the same rules. So we know that now. These right here are going to be our p orbitals. Sorry, I also said this wrong. This is going to be 2. 2, my bad. So S, that's our quantum number for L, and that is going to signify 0. Okay. So kind of weird that we go from 0 to 2, but I'm going to explain now. So now we have the p orbitals, which are over here. And those are always going to hold 6 electrons. They're going to have 3 subshells, and then 2 in each, so you understand that. And then this one's going to be s orbital, and these right here are noble gases. They're stable elements. So they don't form ions or anything like that. They're stable, so they're not going to interact. This is kind of like our base. This is where we're going to like count from, like to or from, when we're trying to figure out the electronic or the electron configuration for elements. And then down here, this is going to be our f orbitals. And these are going to have 14 electrons. You already figured out how those work, 2 per, so you're going to have 7, 1, 2, 3, 4, 5, 6. Then you're going to have 7 boxes, and you have 2 in every single one. When you're drawing your diagrams, it'll look like this, like I explained. You'll have different like this. Okay. So let's do an example now. Now that we know how to count these, let's pull up. Let me pull up here my periodic table and show it to you. And then we'll be finished here. We'll just do a couple examples. So zoom. Screen share. Where is? It's not giving me the option here to share my periodic table. Okay, well, I guess pull out your periodic table and I'll pull out mine, and you'll know what I'm talking about here. So let's just say, for example, we're working with lithium and we want to know what the electron configuration for lithium is. What we do is count. We know that in hydrogen, here, in this element, that's going to be an s orbital. And here we know, so lithium is right here. sorry. So we know lithium is right beneath hydrogen. So lithium is going to be, we're going to count this way. So we're going to have the first electron will go here, then the second, and then the third, and we're going to move that way through the periodic table as we go through it. Move left to right there, just like we read. So the first electron will be in the energy level. The rho is 1, so that's our energy level. And then the orbital is S, and we'll have 1 electron there in this one. And then we have in that same row, S orbital, we have another electron. So we have 1, S2. And then for lithium, it's on the second row. So our N is going to be 2. It's in the S orbital pattern. So we're going to have S. And then there's 1 electron because the atomic number of lithium is 3, which means we are going to have 3 electrons, 3 protons. We learned that earlier. So since we have 2 electrons here, we only have 1 left over to give. We're going to put it in the S orbital. So let's do just a more complicated one here, down with the F orbitals. This is going to be more complicated, and we're going to understand why the noble gases come into play here. So let's just say we want to know here where gold is going to be, AU79. We want to know what its electron configuration is going to be. Let's just work through this together. Gold's on the second to last row. It's going to be right about here. So let's just say these are the last 2 rows in the periodic table. Gold's about right here. But before it comes these radioactive elements, and we count these as F orbitals. So instead of writing down all the electron configuration that starts at hydrogen and moves left to right all the way through the periodic table until we get down to the second to last row, what we're going to do is just use a noble gas, which in this case, the noble gas on the row right above gold is going to be xenon. So we know that xenon is stable. And we can just use xenon in brackets like this to just work from that base so that we don't have to write down all those crazy numbers, even though we might. Professor Morton said that with the longer elements where we have to write out more, it's unlikely that we'll have to write out of them. We'll use noble gases as our base to write out the rest of the number. So xenon, let's just go here. With xenon, we have cesium and barium, which are in the S orbital. So let's write that down. They're going to be on the, count it out with me, 1, 2, 3, 4, 5, 6. They are on the 6th row. So that's going to be our N number, right? 6. And then we know that they're in S orbital. And from here, we're going to write per box on the periodic table, we're going to have 1 electron. So we're going to write the number 2 because we have cesium and barium that are before we're trying to get to gold. So on that line, if you look, cesium, barium are in the S orbital, so 2 electrons there. But then we come in contact with these F orbitals. So down these F orbitals, the way it works is these F orbitals here, when we're counting, their N number is actually equal to, N is equal to their row number minus 2. So the row we're on is 6. So we're on the 6th row, minus 2 is 4. So our N number is going to be 4. And then the orbital is F. And then we know that there's going to be 14 electrons in there. And we're trying to get to gold. So we need to not only go through all of these, so that would give us 14, but we need to go past them now. So the way we do this now is that now we're in the d orbital. orbital we're trying to get now from the end of those radioactive elements from hafnium to gold. So let's get to that. We're left with, so from here now, we've made it all the way to here, down through here. Now we're trying to get to gold. The way to do that, this last little part, is we know we're in a d orbital. So we're going to say, we know that the n is equal to the row number minus 1. So we are in the row number 6 minus 1. So our n number is going to be 5 for here. So we have 5, and then we know that our orbital is d, and we know that they have 10 electrons. Okay, so let's go here. We have gold, so we're going to count out 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to count out 9 from the end of the radioactive elements to gold. So that's going to give us 9 here. And you might think to stop at something that we learned in the book, in the textbook, is that when you get near the end of the transition metals, you actually can't leave this as a 9 because we're so close to 10 electrons, which would fill up all of our orbitals and make it more stable. So what we actually do is that we fill up these d orbitals before we fill up these s orbitals. So we'll actually take one from here and it'll be 1, and then we'll add that electron that we took from here and add it here so that this is stable.